easier than adding and subtracting. So if you got the notes yesterday, today should be A-okay. 2 rules you need to know. The first is when we multiply radicals with unlike radicands, so when the radicands are different. And then what happens when we multiply radicals when the radicand is the same. I should have left a little more space there. That upsets me. Left brains will understand. In your head, multiply 3x times 2y. In your head, multiply 3x times 2y. Just turn and share with someone. What did you get? I heard lots of 6xy's. That's good because that's the answer. So what you did in your head, you just didn't know, is you multiplied the coefficient by the coefficient, and you multiplied the variable by the variable, and when the variables aren't the same, we just smush them together. Exactly the same deal here. I'm going to multiply coefficient by coefficient, so I get an a times a b, or an ab. And then I'm going to multiply the radicand times the radicand, so I get a root of xy. Exactly the same as polynomials. Coefficient times coefficient, radicand times radicand. Coefficient times coefficient, radicand times radicand. Because they're physicists. I don't know. I think it's something in... No. I am in awe. Like, physicists are way smarter than I could ever be. Like, they are smart, but they're weird. They are. So are accountants, just saying. They are.
So like all the math people?
Yeah, should we be like best friends?
Mathematicians are fussy. We're not really weird. Though today we're going to seem a little weird. Architects are fascinating to me. Engineers are fascinating to me. I think if I had a second career, it would be in engineering, I think. Or genetics, because that fascinates me too. Yeah. How our brain works and how are there twins that are so much the same and then so different, and that fascinates me. One that's a little bit different is when the radicands are the same, so root of x times root of x. If you follow this, what you get in theory is the root of x squared. But then what's the root of x squared? X. So any radicand times itself is always just the radicand. What happens is the root ends up disappearing. The second step you need to know is we simplify if possible. That's it. 2 steps for multiplying. Coefficient times coefficient, radicand times radicand. Simplify if you can. Yeah, 2 little steps. Let's do some examples. At first, these seem kind of weird because it's like, there's roots everywhere and there's numbers everywhere. This one is a monomial times a binomial. Quick review of polynomials. What's a monomial? 1 term. What's a binomial? 2 terms. So this is the same thing that you did with polynomials, is we distribute the monomial throughout the brackets, so we multiply it by everything. We don't see a coefficient in front of this root 3, but what do we know is there, but it's not there? It's a 1, so I'm just going to put the imaginary 1 just for the first one so you can see what we're doing. Lindsay, earphone, please. I'd rather you copy this and watch that later. Is that okay? Just because you're going to miss this as well? Okay, up to you. Whatever you need. Okay, so coefficient times coefficient is 2 times 1. Like not a trick question, 2 times 1. And then radicand times radicand, root 3 times root 5 gives us root 50. The second term, 2 times negative 4, negative 8. Root 5 times root 10, root 50. And then we just simplify. Let's look at 15 first. Is there any prime factor perfect squares hiding in 15? No. What about 50? Ooh, what's hiding in 50? So I'm going to keep my 2 root 15. Can't simplify him, so he's just going to stay. I'm going to keep that coefficient of negative 8. And then I'm going to prime factor 50, which we know is 5 squared times 2. What's going to happen to this 5 squared when the 5 comes outside? The squared disappears. I've already got a negative 8 out here, so when I join the 5, what's going to happen? Negative 40 root 2. That's final answer. That's it. That's multiplying radicals. Radical times radical, coefficient times coefficient, simplify if you can. Example 2. There's numbers everywhere. I'm going to show you 3 different methods to this question, and you can pick whichever one you like the best. I don't care. If you've got a different method, that's A-okay as well. Some of these you probably saw in grade 10, maybe some of them you didn't. First one, FOIL. I'm assuming you've heard that word before. Nice. Second one I call tic-tac-toe. You may have seen that one last year. Last one I'm going to call double distribution, which you've probably seen. Doesn't mean you have to know all 3, completely up to you. I just always like to give you lots of choices so that you find one that works with your brain. I'm going to do FOIL the long way, which you probably didn't do last year, and that's fine, but just so everyone can see what's happening. So I'm going to put down the letters F-O-I-L. The 2 first terms will be 2 root 3 times root 3. The outside will be 2 root 3 times negative root 2. The inside terms is 3 root 2 times root 3. And the last term is 3 root 2 times negative root 2. Coefficient times coefficient, radical times radical. So here I have 2 times the imaginary 1, which gives me 2. Root 3 times itself. Now be careful because you're going to say root 9, but then go one step further. What's the root of 9? 3. So that's that root 3 times itself equals 3. And then I'm just going to do 2 times 3. 6. Which it bothers me so much it's on the line, but I'll deal with it. 2 times negative 1 is negative 2. Root 3 times root 2 is root of 6. 3 times imaginary 1 is 3. Root 2 times root 3 is root 6. 3 times imaginary 1, imaginary negative 1 is negative 3. Root 2 times itself, root 4, but then go one step further. What's root 2 times root 2? It's 2. And when we simplify that one, we get negative 6. So describing those 4 terms, I have a negative 6, I have a negative 2 root 6, a positive 3 root 6, and a negative 6. Simplifying, what's going to happen with 6 and negative 6? It's going to cancel. Can I combine these 2 root 6's? Yeah. So if I have negative 2 of something and then 3 of something, what do I have? 1 of something, so I have a root 6. Like, is that not crazy mathematically that all of this crap up here all comes out to be root 6? It's kind of crazy. You don't need to do FOIL with these 4 steps. If you can jump right to here, great. I'm just showing everyone where the steps came from.
So what do the 4 letters represent?
First, outside, inside, last. It's pied in French, so première, antérieur, extérieur, dernière. So same thing, just in English, FOIL. Tic-tac-toe is I'm going to draw a tic-tac-toe board, so the 2 horizontal lines, the 2 vertical lines, so it makes 9 spaces. I'm going to put a multiplication sign in the upper left, because that's what we're doing, is multiplying. I'm going to write the first binomial across the top, one term in each box. So 2 root 3, and then followed by 3 root 2. I'm going to write the second binomial down the side, one term in each box. So a root 3 times a negative root 2. Then I always like to change color because I'm a color person. And all I'm going to do is multiply the intersections. So 2 times imaginary 1 is 2. Root 3 times itself is 3, and I'll simplify that in a second. 3 times imaginary 1 is 3. Root 3 times root 2 is root 6. 2 times negative 1 is negative 2. Root 3 times root 2 is root 6. And the last box, 3 times negative 1 is negative 3. Root 2 times itself is just 2. And so now I grab these 4 kind of in the bottom right quadrant. So I have a 6, a plus 3 root 2, a minus 2 root 6. This should be 6, sorry. And then a minus 6. And if you take a look to the left and look to the right, exactly the same step. It's just how we got there is different. This is FOIL. It's just doing it in little compartments, which left brains tend to like. And so when we simplify, we're going to get root 6. Have you seen tic-tac-toe before? Okay, if you've seen it, great. It'll work with x's as well, so even without radicals. Tends to be a little more left brain because we like spaces to put stuff. Double distribution is where you use the arrows. It's a little more right-brained. And so I'm going to go first. 2 root 3 times root 3 is going to be 2 times 3. 2 root 3 times negative 2 is going to be negative 2 root 6. 3 times 1 is going to be 3. Root 2 times root 6, or root 3 is going to be root 6. And then negative 2. Negative 3 times 2. Oh, it bothers me. I can't squish it in there. That's a negative 3 times 2. And so simplifying that, I get 6 minus 2 root 6 plus 3 root 6 minus 6. And compare exactly the same step, just different how we got there, and then a root 6. This is FOIL. We just did the terms in a different order, that's all. I do not care which method you use. I don't care if you have a different method. As long as you can get the answer, pick whatever one you like better. Because these are the first, and then these are the inside. No, it's the outside. No, it is the same order. Yeah. Sometimes I do I before O. I don't know. Just remember it works. Yeah. Number 3. Okay, now I'm smelling like onion soup, maybe? Onions? Onions, I think? Maybe. Maybe it's weird. I'm going to first show you the wrong way to do this question, and it's completely up to you. Some people don't like to have wrong ways in their notes. Some people like to have it as a visual reminder not to do it. It's completely up to you, but someone is going to do this on the test, and someone is going to do this on the final exam because I see it over and over. So this is the complete wrong way to do this question. I'm going to distribute this exponent. So a root 3 squared is 3, and a root 6 squared is 6, and therefore this has to equal 9. Why not? I did some math stuff in there. Why? Natasha?
Because the exponent is outside the bracket, so you gotta finish what's inside the bracket and then use the exponent.
High five. There's an exponent law that kind of looks like this, and it's usually what's going on in your head. And the exponent law looks like this: xy to the n equals x to the n, y to the n. So we've kind of done that distribution thing before, but there's a huge difference between these mathematically. What's the difference? Besides that, this is a binomial, this is a monomial. There is no exponent law that deals with a binomial. There is no exponent law that says x plus y to the n. It doesn't exist. So you can distribute when you're multiplying, you cannot distribute when you're adding. So this is the complete wrong way to do it. And somebody's going to do it because you're used to this. And that seems like a really good thing to do in your head. What do you do then when you have a binomial squared? Just write it out twice. Once you write it out twice, it's a little bit easier for your brain to see this is either FOIL or tic-tac-toe or double distribution. Pick the method of your choice. You can do any method you want. Pick whichever one you want. Do this question for me. How? Yeah, if you could, then you would, but you can't in this one. Whether you double distributed, whether you FOILed, whether you tic-tac-toed, this is where you should be before you do any kind of simplifying. So everyone should be on that step, however you chose to get there. Any question where any of those 4 terms came from? Right, any root times itself ends up being just 3. You can go to root 9 if you want to, but then the next step is root 9 equals 3. Yep, you're just a step ahead of me. I just haven't simplified yet. I'm going to simplify the 3 and 6 together, which gives me 9. And then I have 1 root 18 and a second root 18, so I'm going to have 2 root 18. Oh, but we're not done. No, why not? 18 should jump out at you. What's the perfect square factor in there? So how can we write this so that we can simplify it? And what happens to that squared when the 3 comes outside? Cancels. What happens to the 2 that's out there already when I put the 3 out there? So I get a 6 root 2. There's your final answer. 9 plus 6 root 2. Show me your thumb. I'm getting this. I'm kind of getting this. I'm not getting this. Good. Go on to crazy number 4 when we stick in variables. Why? Why did the world have to put letters in math? Ooh. I'm going to double distribute because I feel like it. So 2 times imaginary 1 is 2. Root of x times itself is just x. 2 times negative 1 is negative 2. Root x times root y is root xy. 3 times 1 is 3. Root y times root x is root xy. And 3 times negative 1 is negative 3, and root y times itself is y. So I'm going to put those 2 xy's together. So I'm going to have my 2x that's still there, my negative 3y. And I don't care the order. 3y's in the back, that's fine. Order's not important. If I have negative 2 of something and 3 of something, how many somethings do I have? Again, I'm not too concerned with the order. If you've got the 2x first, great. If you've got the root xy second, whatever, as long as you have those same 3 terms. Those are all the different multiplying questions you're going to see. You're going to see a monomial times something in brackets. You're going to see a binomial times a binomial. You're going to see a binomial squared. And then you're going to see binomials when they have variables instead of letters for the radicand. I just pointed to all that, and you couldn't see any of it. I did some very nice pointing, though.
Why is it negative 2x? I think I did something wrong.
I don't have a negative 2x.
Or I mean,
Miss Thompson,
I mean,
you
like,
said variables instead of letters.
But they are variables.
No, you said you're gonna see variables instead of letters.
Instead of numbers. Very good.
sorry, I meant the negative 2.
Here?
Yeah.
Because I had a 2 times a negative 1 here.
Oh, I see. Okay. So the
You know me fairly well by now. We've been together 3.5 weeks. Do you think I love math? I really love math. I get to do this every single day. But there's some things that are just stupid. And this is one of them. It's just stupid. And I don't get it. Well, I get it, but I don't get why we do it. And it's one of those, the government says I have to show you, so I will show you. But it doesn't even make sense. Just go with it. Mathematicians were fussy people. And when I originally typed the notes, I put fuzzy. We might be fuzzy too, but we're fussy people. And we don't like radical expressions when there's a radical on the bottom. It just bothers us. Why? I don't know. It just doesn't look right to us. It's kind of like if you wrote x times x. We would never write something with x times x. How would we write that? X squared, right? We just like the way that looks better. What about x plus x? I'd never just leave x plus x. How would I write that? 2x. There's just things in math we just don't like, and I just don't like this root 3 down here. Yeah, we're just fussy people, and we just don't like it. So how we get rid of it is really what dividing radicals looks like. That's why I didn't call this division, even though when you look at the examples, it's division. It's called rationalizing. Rationalizing is when we get rid of the root on the bottom. Why? We just don't like it. There's really no reason other than that. We're going to look at 2 different types. The first is when you have a monomial at the bottom. The second one is when you have a binomial on the bottom. So we don't call it dividing because we're not really dividing. All we're doing is just changing what something looks like. I'm going to completely change this expression so that there isn't this root 3 on the bottom. I'm going to do something to it so that I get rid of that root. Why? There's absolutely no reason other than we just don't like it. So to rationalize a radical expression, multiply the top and bottom by the radical in the bottom. Radical in the bottom. You might want to put the title rationalizing, but it's completely up to you because I renumbered the examples. I went back to number 1. Because there were like 2 sections, so I went back to number 1. That's a 1. It's a number 1. So 6 divided by root 3, like literally I can't even say it without getting the shivers. I just can't deal with that root on the bottom. I just don't like it. So what I'm going to do, I'm just going to times the top and bottom by root 3 divided by root 3. What now? What? Why mathematically can I just multiply by something? So what is the only number that I can multiply by that doesn't change the original number? What is the only number mathematically that I can multiply something by and not change it? 1. So that's the only time in math I'm allowed to just throw a number in there, is only when it's equal to 1. Well, what is root 3 divided by root 3 equal to? 1. That's the only reason mathematically I can do this. If that was equal to something else, I could not do it. But I know if I multiply by 1, I'm not really changing the value. This is now 2 fractions. Let's quick review. How do we multiply fractions? Top times top, bottom times bottom. So the top is going to be 6 times root 3, which is equal to 6 root 3. On the bottom, I have a root 3 times itself, root of 9, except what is root of 9? And then I got these coefficients hanging around here that I can just simplify. So what is 6 divided by 3 equal? 2 root 3. Grab your calculators. Yep. Yep. Yep.
I never really understood why you would just do that. Like, why didn't you just divide 6 by 3 without dividing the root?
because this is all multiplication. So if I wrote it like this, it means the exact same thing. And so all I'm really doing is just reducing this fraction because it's all multiplication. I want to know the decimal value of 6 divided by root 3. So the original question, get me the decimal value. 6 divided by root 3. And don't round off. Give me a whole bunch of decimals. They make me happy. 6 divided by root 3.
1.7320.
Oh, we got two different values here, so let's just fight it out. Remember, if you're on the old operating system, you might have to close off that root 3. So 6 divided by root 3. 3.46 something. Can we just confirm that? Okay. Now I want you to do 2 times root 3. It's the exact same thing. That's because I didn't change the value. I just completely changed what it looks like. Why? Because we're picky people. That's the only reason we just don't like it. I know, it's crazy. I told you it's going to make us look weird. We just don't like it. I did not change the value. The value is still exactly the same. I just changed what it looked like. Let's do number 2. 2 root 3 divided by 3 root 5. The 3 on the bottom does not Again, I'm a bracketer. If you don't need the brackets, don't feel you have to. My brain just sees FOIL better when I have brackets. Another handy thing to do, especially if people are not visual, this can be visually overwhelming. So if you just cover the bottom, sometimes it's a little bit easier to do the top, and then you can cover the top and just do the bottom and then find out what's going to happen. So FOIL, root 2 times root 2. 2. Root 2 times 1. 1 times root 2. 1 times 1. Whoa, 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 whoa. I told you those radicals had to cancel. What? No, but we wrote a note about that. Only on the bottom. So don't panic on the top. I don't care about the top. I only care about the bottom. So if they don't cancel on the top, no biggie. Okay, now let's just do the bottom. Root 2 times root 2. Root 2 times 1. Negative 1 times root 2. And negative 1 times 1. Did my radicals cancel? Then we know everything's happy and we're good to go. Okay, the top. Let's clean it up. What do I got going on here? Well, I got some whole numbers. I got a 2 plus a 1. And then I got 1 root 2 and I got another root 2. On the bottom, those roots canceled. Woo, woo, because we want that to happen. I got some numbers hanging around, though. 2 minus 1. Do I need to write that 1? Why not? So what's the final answer to this question? Now tell me, doesn't your brain even see that this is prettier and nicer and way more simple than this? This is pretty, no fractions. We don't like fractions. That's why we rationalize.